You should be able to hear me now.
Yes, now I can hear you.
Apologies for that. Okay, so I was saying today we're going to be talking or having a discussion on uninformed searching, right?
Okay.
This discussion centers around, remember, we had this definition of searching. We said searching is that when we move from a problem to a solution, that process is what we call searching, right? So we're just gonna go through different searching strategies, and hopefully should be able to answer some questions. Right.
Okay.
So we said goal formulation. These definitions we done. We said based on the current situation, right? Goal formulation is the first step to problem solving. And then problem formulation is the process of deciding what actions and states to consider given a goal, right? And then what I want is the process of looking for a sequence of actions that reaches the goal is called a search. So searching is the process of looking for a sequence of actions that will eventually get to the goal. And then we have what we call a search algorithm. So it is a black box, called a black box, that takes in the problem as an input, and it will give action or multiple options of getting to the solution as an output. Okay. So that is searching, and that is what we're going to be focusing on. So today we're going to be focusing mainly on uninformed searching. Right. We define the problem into 5 components: the initial state, actions, right? Transition model, and goal test, and the path cost function, which we used in the questions that we responded to last time. And there is another important definition, maybe not so much here, but abstraction. We look at abstraction when we want to remove elements that will not really affect, or even if they do affect, right? Think of it when you're driving. If you hit a small pothole or a small dent on the road, right? It is not generally going to affect the motion of the car. But if it's a really big pothole, then it can even veer the car out of the road. So abstraction, we are then looking at these so-called potholes and seeing which ones are necessary to look at, which ones have got the capacity to change the direction of our motion. Right. So abstraction, we are removing unnecessary detail, or from our model, we are removing some detail. So we will still have a model that represents the actual situation, but it will not take into account all the factors at play. Right. So state space problem, we know, is the initial, the actions, and the transition model. Right. So uninformed search algorithms, right? These are sort of a general purpose, or we can call them brute force search algorithms, right? They do not have additional information. So we're saying go blind, try to get to the solution without any prior information, right? So it makes them not efficient, but also they are still able to solve some of the most common problems in modeling or artificial intelligence. Right, so we're going to look at the following. So we have got breadth first, uniform cost search, depth first stage, depth limited, iterative depending, and bidirectional. So we're going to look at these in detail and explain what each and every one of them entails. Right, so breadth first, this is the most common, right? We use it mostly when we're traversing a trio graph, which are the most common types of problems, right? This strategy searches breadthwise. So what does it mean? It means that if we have got multiple levels of our problem, right, it will start by finding the solution on the first level first, right, and then it will move on to the second level, right? It will not search for the solution on the third level before it has searched the prior levels. So there is no way that we are going to find a solution that is here. If you've got multiple solutions, say for example, you've got multiple solutions, you're not going to find this solution first before you find this one there. So that is why it's called breadth first. So it goes, it searches for the solution level wise, right? So also it's and there's some terms that we're going to learn now that help with these strategies. So from the root node or from the start state, right? Your breadth first search is going to expand the root node at the current level, or the successor node at the current level before moving to the next level. So if you are here, right, you are going to, how can I explain it in simple terms? But we are going to look at, let's say, completeness, right? We're going to look at the time factor of each and every one, the time factor, and this space factor as well, to judge these search algorithms, right? So we're going to use a FIFO structure, a direct queue for this, right? First in, first out. Also, what you realize is that it is going to test, right, before expanding. And so we're going to look at expansion. These are the terms to look out, and they become very important once we describing or looking at the advantages of each. So we're going to look at expansion, and then we're going to look at expanded node, and we're going to look at also the frontier, right? Right. So, right, this is breadth first search in action, right? So, say our goal is to find K. You're starting at level 0, which is your root node, right? From your root node, right, it is going to have you take S from your root node, right? It is in what we call the frontier, right? So what is the frontier? So our queue is in such a way that S is at the top, right? The frontier is any, or is a hypothetical front where elements that are going to be, or that are due for expansion, or that are due to be dealt with next lie, right? So that's what we call the frontier. So now looking at this, we start off with the root node S, right? When we expand S, right, we said, on our C strategies, we have to test whether or not it is a goal, right? So when goal testing happens, also determines the model that you're using, right? So you can test whether or not it is a goal. Number one, you can do it before expansion, right? Or two, you can do it after, right? So after expansion, normally what happens is, so before you expand, is it a goal? If it is a goal, then you stop, right? Or after expansion, what do you mean? We say we just go and we say, okay, cool. After we have we expand this, it gives us C and D, and then we check whether or not it is a goal, but it is already given as successor nodes, right? So goal testing happens before expansion. So what happens is you start with S goes to the frontier, you expand, S goes to your solution set, and then you now have A or B in the frontier, right? A got into the queue first, and then you expand A, right? And then A goes into the solution space, and then you go to B. B is in the frontier now. So since A is not a solution, it adds on C and D, right? But B got into the Q first, so it's going to be expanded next. So B gets expanded. It's not the solution, but when B is expanded, it gives us G and H, right? So in our frontier, we now have C, D, G, and H. Right? C got in first, so C comes out first. So we're going to have C, right? It moves out of the frontier. It's expanded. Once it does that, it gives us E and F. Right? It gives us E. It will give us F, and then we end up having now D gets expanded, right? So you follow the logic to say it's B, C, D, but then all these are now being added to the frontier, and because D was added first, it has been taken out, expanded, right? Before you get to E and F, you've got G and H that came in first. G would then be expanded and join the solution space, and so forth. H will follow, then E, F, and then I, and then you're going to have K, right? So that is how breadth first search works, right? That is how breadth first search works. So we have to say just before expansion, before expansion, right? And after generation or upon generation. Right. So those are the two. You expand just before expansion or when it is generated. That's how you test a goal. So the advantages of breadth first search, remember I said to look out for these words. These are going to be our performance measures. Right? So a breadth first search, we're saying it is complete. We say a search strategy is complete if it is going to provide a solution given that it exists. So if there is a solution for this problem and it exists, a breadth first search we will find it. We say that breadth first search is complete, right? It is also optimal, right? Where the solution is finite, where the search space is finite, right? So if there is one, if there are more than one solution for a given problem, right, it is going to find the most efficient one. So we say it is optimal. So optimal is efficiency. You find it with the smallest cost function. So smallest cost function. Smallest cost function. Right. So we say it is optimal. So how do we look at it that way? Because it goes on level by level, right? It will find the solution at the shallowest level, with all other things being equal, the path cost function being equal. Right. So those are the two advantages associated with breadth first search. The disadvantage is that it requires a lot of memory, right? So when the branch goes bigger, right? Because it is required to keep memory of all the levels that it has gone through, right? It will not erase. It will not use the same memory elements. So you are required to keep track of all the states that you've gone through. So it will then require a lot of space for you to implement such a search strategy, right? So because of if the root node is far away from the solution, then the time complexity will be exponential as well, because it can branch up or the branches become more and more. So the space complexity is exponential, right? And the time complexity is exponential. So you find that if you have got a 32 level search space, you're going to see that, say you have a branching factor. So branching factor is defined by the average number of branches. Let's say you have got 3 to the power of 32. This would then be your search space or your space complexity. Right? Same as the time complexity. And you're saying if an action takes 1 second, right, at minimum, you're going to have 3 to the power of 32 seconds to implement the stage strategy. So the time here can grow really exponential. So it works really well when you have got small stage spaces, right? So that is breadth first stage. So we're going to look at examples of how this works, right? So uniform corsage, when we have a weighted tree or graph or weighted stage space, right? So when I say weighted, I mean to say you know that a specific path from point A to point B, it's so many kilometers, or it's so much amount of money and stuff like that. So you have a weighting of all the different paths that at your disposal, right? So this when you use uniform corsage. So you are not now, instead of following the level by level, you're saying that you are assigning or arranging the frontier not based on a FIFO queue, but on a priority queue that is based on the cost function of the weighting allocated using whatever measure you're using to, whether be monetary wise or distance wise or happiness wise, right? So the key thing here is that you are arranging your queue, not FIFO, right? But based on a priority queue, depending on what it is that you want to achieve, right? So, say for example, if it's a distance, right? Distance issue, ideally you want to travel the least kilometers. So you are going to expand that which has got the least distance covered so far. That is how you're going to do it. Right. So let's start first by going through the search tree. So say you have got this, you have got S, and you've got the goal G, right? So S will be tested, right? We expand, it will give you A and B. But before you do A, right? Before expansion, you test, is it the goal? No. You expand, it gives you, so now you have A in your solution space, right? Right, so you've got B. Once you expand, so you've got S and A, sorry. Once you expand A, it's going to give you C and D, right? So B is equals to 4, C is equals to 4, C is equals to 4, and D is equals to 3, right? So now what is it going to do? It sees B4, C4, and D3. It is going to expand D next, right? So to expand D, right? And upon generation, right, it realizes G, right? So when it realizes G, then it go test and find out this is the goal and it stops. So this one, it is going to test for goal, test for goal upon generation. When a state is generated, that's when it is goal tested. When a state is generated, that's when it is tested, whether or not it is the goal for this specific strategy. Right. So that is how it works. Now let's look at the advantages. It is complete if a solution exists, it will find it. It is optimal because it is going to find the one that is got the least. It is designed, or rather, it is going to get to the solution in the least possible number of steps. If the goal is to minimize, it will minimize. If it's to maximize, it will maximize. Right, and then it also does not care about the number of steps involved. Right, you can have one big step that has got a mark of 40 or an allocation of 40, and you can have 60 or let's say 30 small steps with an allocation of 1 each, it will not care about the number of steps, but about the cost function involved. Right? And then the time complexity. So here, if you have C star as the cost of the optimal solution, and epsilon, right, is each step to get closer to the goal node, right, you'll find that the number of steps will be the cost over epsilon plus 1, right? Because we start from 0, right? We start from 0. That's why we ended at epsilon plus 1. So the time complexity is going to be 1 because we're starting from 0 plus the cost. And that will be the time complexity, right? For the same logic, you're going to have the same for the space complexity. You're going to keep the 1 starting from 0 plus this the optimal cost, the cost of the optimal over the number of steps. So here we're not counting levels, same as the breadth first, where we're saying we're counting down the levels, but we're saying the cost over the number of steps taken. Right? So if you take 1 step, that is 40 from my previous example, so you have 40 over 1, right? And if you have 30 over the same 40 over 30 steps, you find that you're going to have a difference in the space complexity and the time complexity involved. All right. So that is there. Now you calculate the time and space complexity for uniform cost search. All right. Then depth first search algorithm. Now, this one is what we normally use where we use intuition, right? Think of it if you're traveling on foot and you come across a path or a crossroad, and there are 3 roads. Very few of us go and say, okay, I'm going to walk 100 meters down here and see if I reach my goal. Then you do it, you come back and you walk 100 meters down the second road, you come back, you walk 100 meters down the same road, a different road, right? Most of us, you choose a path and then you find. After you've walked and found that, oh, possibly not, then maybe you change your decision, right? So this is what we call the depth first search algorithm, right? It starts at the root node and it will follow the path to the depth node before moving to the other node, right? So here we're going to use a last in first out queue structure, right? And let's see how it works. Come back here, right? So you're going to have S coming in, right? And then it's going to be expanded. Once it's expanded, you're now going to have A and H, right? So assuming A was the last one to go in, A will be expanded, right? When A is expanded, it gives us B and C. So you see that H is the first one in, or H was already in there. Right? The last one to go in will be the one that's expanded. We take B out, it will take B, and then once B goes out, we're going to be left with D and E, right? And then it will go to D. D does not get expanded, it goes to, because B is done, the next one, the last one that was put in is going to be E, so it's going done. B is done, A is done, then C is the second from last one coming in, and then when C is expanded, it gives us G, which becomes the last one in, and then it is expanded. And then it is the goal. So we can test whether or not it is a goal when it is generation. We can test whether or not it is a goal. So that is depth first search. So it is going to go by it's going to use each and every pathway up until it reaches the end. What problems do you think are going to come across this type of strategy? Right? It has some advantages. It requires less memory as it does not remember. So once it has done this branch, right, it will forget. You can use the override with the same memory elements again with new information, right? Because you don't need to remember all that remembers it's been done, right? So it requires less memory. So instead of a what you call it, exponential space complexity, it then has a linear space complexity because you can reuse the memory elements. The time complexity, however, is too exponential because same as breakfast stage, right? If you have got 5 branches and it is on the last branch, it means you have to go through all the branches. So you used to use the same time rather to find the solution, assuming the worst case scenario that it is found on the last branch, right? Then the disadvantages is that it is not optimal, right? There's a possibility that how can I put it? If you have got multiple levels, right, you can go through branches, right, while the solution is here on the first level, right? There might be a solution one step away, but you have to go through 5 different branches with the 1,000 levels, right? So it's not optimal. And then the only time that it is complete is when it is finite. As long as it is finite, or we say it stops at level 50 or level 999 or whatever, as long as it is finite, there's a number to the levels that you can go down, then it means that it is complete. It is guaranteed to find a solution if it exists. So that is the first stage. Right. Then depth limited puts a limit. Right? Depth limited is a depth first stage algorithm, right? But it comes with a predetermined limit, right? So this removes the possibility of an infinite path, right, on the previous strategy, right? But also this is introduce a new problem to say if you're digging for gold, you may just give up like 30 centimeters before you hit your gold, right? So because you are not going to drill further than 10 meters. So if you dig 10 meters, the treasure or the gold might be at 11 meters, but you stop at 10 always. That's the disadvantage of depth limited as well, right? So it will terminate with 2 conditions of failure, right? So when a problem does not have a solution, or the cutoff, there is no solution at the cutoff limit, right? So that's when it terminates in terms of failure. So the fact that it terminates and doesn't find a result does not mean the problem itself did not have a solution. Right. So it's memory efficient. It combines the benefits of depth first and breadth first. So it is memory efficient. You've got a linear memory allocation, and then it is incomplete when it's above the limit. It may not be optimal if the problem is more than one solution. Yeah, so if the problem is more than one solution, it may not be optimal. The other solution might be below your limit, while you have to look for the other branches to get to your solution. So that's that. So depth limited, we're going to limit it to level 2. The solution is J. So you're going to use the first stage up until, but you're not going to surpass level 2. Every time you're going to stop when you get level 2 and then you come back again. Right? So that is depth limited algorithm. Right? So you also get when it is generated upon generation, that's when you you go test when A state is generated.
I could just on that diagram.
Yeah.
Yeah, if solution is not on level 2, what's going to happen on this one?
It is not going to retain a solution. Say the solution was AG, and there is no, the limit is level 2. It is going to retain the solution, and it is going to retain and say no solution found. So remember they said here there's 2 conditions for termination or conditions for failure, right?
Yeah.
The problem does not have a solution or no solution for the problem within the given depth limit. So it will come back and present this as an output.
Okay, which means on this one, then we give up easily.
Yes.
Okay, no, I get it. Thanks.
Yeah. Then iterative dependence, the passage. So now we are now getting clever with how to go around this. So what happens is then they say, okay, depth first is too wild. We don't know how when to stop. Then we have the one that we just done now, right? We're looking at depth limited. It imposes a limit. It may be too shallow. The limit may be too shallow. Then they came up with iterative depending depth first edge. So what it simply does, it says, okay, we're going to set the depth level to 1 for now. Then we're going to come to 1, right? And then we search 1. And then we go to the other branches at level 1. Then we search the depth level to 2. So we're going to say that, and then we come back and then we put this, that, and that, right? So after that, if you don't find a solution, you set it to 3, to 4, to 5, to 6, to 100, right? So we are continuously increasing the depth of our search at each iteration. So if I do 1 and I don't find a solution, I'm going to throw that away. Then I'm going to put it to 2. Then I'll use it again. And then if I don't find a solution, I throw it away, right? So we have the benefits of breadth first search and depth first search memory efficiency, in that we can throw away what we've done, right? Once we set the iteration to 2, we don't care about the iteration at 1 now, right? And once we are doing that, we're still going to have sort of a breadth first search, because the breadth is now limited, or the depth is limited to 2. You have to search everything that is in at level 2 before you proceed, right? When the search space is large and the goal depth is unknown, then iterative depending can be an option, right? So it combines the benefits of this. So we have got fast search and memory efficiency, complete if branching factor is finite and it is optimal, right? So it's going to repeat all the work of the previous phase. That is not a good thing. It's going to repeat it because it doesn't keep memory. It's going to repeat. Right. So iterative depending, it's going to say level is equals to 1, search, right? Then no solution. Level is equals to 2, search, and then go. Then it will stop. That's now iterative depending. All right. The last one becomes a bi-directional search, which is something that can be, let me find a way to put it. So for example, you want to build a bridge over a 20-meter width river, right? So all along we've been building our bridges starting from one end and up until we get across the river. Then we've got a clever someone who comes and says, but guys, you know that you could spend half the time building this bridge if you've got one team starting from one end and the other team starting from one end, right? It's all nice and, efficient, right? To do it, as long as you guys are aligned, right? What happens is if there's a small alignment, then there's not going to be a bridge that most people are going to be driving over. So bi-directional search, we're saying one, you have a search strategy, you are starting at the same time from the initial state and from the goal state. So this one requires that you already know the goal state first so that you can go and start from there. So one is starting from here and the other is starting from there, and they're going to meet likely at the middle. And then, once they meet, you can stop the search. Right. So bi-directional is not limited. You can use breadth first, you can use depth first, or uniform. It is still fine. And as long as you're coming from both ends, then you're going to have a bi-directional search. So it's almost never used except for when you've got more information about the problem, then you can go ahead and use it. So the search is fast because you're going to have the time for you to get to the middle, right? It requires less memory, right? If you're using depth, it actually depends on if you're using depth first or breadth first, right? The implementation is difficult because alignment is everything. Think of the example of a bridge. If you go out by 5 centimeters on the alignment, then that's not gonna be a good bridge, right? So you need to know the goal state in advance before you use a bi-directional search. Right. So all these are what we call uninformed search strategies, where the only information that you have is what you're provided. So this is the root node, this is the goal node. You start from there, you start from there. When you meet at the intersection, then you say you found your solution. Right. Right. So any questions? So
no question. I understand it. We also have the bridge like this that get complete in Cape Town.
We also have
a bridge that was not completed because of this. It was out of alignment in centimeters.
Yeah. Yeah, so it works like that. If you are also starting from your side and I'm also preparing on my side, then yeah, we will meet at the intersection node there. All right. Yeah. So okay, what was I looking for? Looking for something here. But I wanted to see if we have time for a question at least. A question at least. All right. Let's have a look at something. But from the assignment, for example, we can say, we can look at question 2. Question 2. So let me just take question 2 here. It says, there we go. So it says, what are the differences between a tree and a graph? So a tree, as the name suggests, extends, right? in one direction, whereas a graph is multi-directional. Right? That is the difference between a tree and a graph. A tree is unidirectional and the graph is multi-directional. Right? So right. So say breadth first search differs from the general tree search algorithm. What is the right? So I can see properly here. How does breadth search first differ from the general tree search algorithm? Right? What is the major reason for implementing this algorithm this way? Provide an example in the discussion. General tree search algorithm. So breadth first, we say it goes breadthwise first, right? Ooh. All right. So in breadth first, you can do graph search. You can go multi-levels at the same time. Here they're describing the general tree search is where you have to go up a branch. So they're differentiating between breadth first search and the depth first search, right? So where do they differ? They differ in terms of the space complexity, right? Because breadth first you're required to keep memory, whereas the tree search you're not required to keep memory, right? So you can then give example to say if you're using breadth first, you have to keep memory of all the nodes that you have gone through, but depth first, you do not have to keep a memory of branches that you've gone through. So you can reuse the same memory elements to continue with the search. Right. Then if we look at right. The graph below, sliding block. Let's see if it asks the questions that we wanted to ask. It says, right, let's put it here. Consider an example of a sliding block puzzle, right? Game stated below figure 1. How many distinct states are there for puzzles of this sort? How many search nodes? Explain how you reached your answer. Right, so what are they saying? How many search nodes? So it's a sliding block puzzle. Right? What are the options? Right? What are the options? How many search nodes can you have? Right. So normally a sliding block puzzle is you're going to have one open space here, and you're supposed to move everything to make a word, arrange it in some sort of way, right? And then maybe from A to, I don't know, the 16th later or whatever the case is, right? So what you do is at any given point in time, you can have up, down, left, right. You see, so this space can move up, it can move down, it can move right, it can move left, right? So how many search nodes? You're going to have 4 search nodes, right? How many distinct states are there for puzzles of this sort? So distinct states, you're saying you're going to have how many levels? So each item can move, so 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. So you're going to have 4 to the power of 16 variations, right? For each and so that's how many states you're going to have. And then you're going to have 4 nodes, so at each stage, you're going to have 4 nodes, 4 nodes, 4 nodes, 4 options for each one, right? So it's 4 to the power of 16, right? So that's how you answer to that one. And then if I can see, I wanted an example of us doing an uninformed search strategy. Seems okay. So it's question 5. It needs us to do iterative deepening. So that is where we start off. From next class, we're going to do some questions, and then before we move on to informed search strategies. So question 5 is the iterative deepening. And yeah, I think we'll be able to complete question or assignment 1. But before then, I'll send you my sample solution of assignment 1 that you can use as well with what we've done now. So you should be able to do question 4, right? Question 4 we done together last week. Question 5 you should be able to try. Question 3 you should be able to do. Question 2 just definitions, and question 1. So what is the purpose of an explode set? Right, an explode set, it shows you what has been, what has been said, what is not part of the solution. What is part of the solution is the explode set. Types of queues that may be employed in SH, C4 and LE4. Then you've got the priority queue, right? List and explain measures used to determine problem-solving performance, right? So we're looking back to the earlier notes that we started. So if you would like to, you can also start writing. This is a bi-directional approach. Start your assignments, send me what you think are the correct solutions. I can guide you. And then I'll also send my guidelines of what I think this assignment solution should look like. All right. Questions?
Could you please just upload the previous video, the recording?
Oh, that one, yeah. I'll follow up and find out if it has been, what's the delay? Just follow up with.
Yeah, okay. I was also gonna say I didn't see them. I didn't see them.
Okay, no, it's fine. I'll put more pressure on them to upload.
Okay, no problem then.
All right, thank you. Enjoy the rest of the evening. Good night and goodbye.
Thank you. Cheers.
Bye.